Hello, welcome to the webinar. Thank you for joining us. My name is Andrew Mills, and I'll be introducing this webinar and then handing it over to Naeem Dargouth, the primary author. Just a few housekeeping items before we get started. The audio for this is muted, and so we do intend to have some time at the end of the presentation for question and answers, but the way to do that is to use the chat function in the bottom left of your screen. I'll be monitoring that during the presentation, and then we'll collect those and then ask the questions at the end. This webinar is being recorded, and at the end of this, shortly after the completion, we will post it on our website so that you can have access to it and share with your colleagues if anyone else is interested but wasn't able to make it. We also do have the slides available online. You can go to our emp.lbl.gov website and find that through our publications page. And with that, I will hand it over to Naeem to do the presentation. Thank you.
Great. Thank you so much, Andrew. And thank you for everyone for having joined this webinar. My name is Naeem Dargouth. I'm a researcher in the Electricity Markets and Policy Group at Berkeley Lab, and I'll be presenting today on our recent report, The Implications of Rate Design for Customer Economics of Behind-the-Meter Storage. I'll be leaving some time for the Q&A session at the end of the talk, and as Andrew said, please type your questions as we go in the bottom left kind of chat function. All right, great. So let's get started. So just a basic outline of the presentation today. I'll be starting with an overview of the project, giving some context to the work. I'll spend a fair amount of time on the data and methods before delving into the results, starting with explaining the demand charge savings from behind-the-meter storage, then the energy charge savings from storage, before finally giving some high-level conclusions from this work, as well as a slide on aligning interests, and that's a bonus slide, as we'll see. So as we've seen, rates are evolving due to a number of underlying factors, largely driven by distributed energy resources, but also technological developments. Customer-sided storage, which is a relative newcomer, is not yet widespread in adoption, given its price, generates most of its value by exploiting specific features of retail rate design, which allows storage to reduce electricity bills. In fact, electricity bill savings from behind-the-meter storage are really closely linked to retail electricity rate design. Because of its low penetration levels, rate design has more of an impact on the customer economics of storage than the other way around. And as regulators look to balance policy objectives related to the rate reforms we've discussed and storage deployment, it's going to be essential to understand how proposed changes in rate design may impact the customer economics of storage. There has been some previous work that's looked at the customer economics of storage, but those have focused in large part on the demand charge rate as the driver for bill savings. Yet there are these other aspects of rate design beyond demand charge that can be critical to understanding the behind-the-meter storage economics. And this includes the details of the time-varying energy charges, as well as net billing rates for solar PV. So the study that I'm presenting on today is really looking to fill those gaps in this previous analyses, and hopefully will provide some insights into which rate designs are most important to the customer economics and market potential of behind-the-meter storage. So the objective of this study is to explore how the details of retail electricity rate design can impact customer bill savings from behind-the-meter storage. So to be clear on the scope of the study, the focus is exclusively on the customer economics of storage. So also interesting but not considered here is the value of storage deployment to the utility and how well the storage deployment used to maximize bill savings aligns with the optimal storage deployment for the utility grid. So those two things may be considered for future work. Also, we focus on the utility bill savings from the demand charge and the energy charge portion of the bill, we don't look at potential value streams for behind-the-meter storage owners, such as participation in wholesale markets, customer reliability and resilience benefits, voltage support, utility investment deferral, et cetera, though some of those may be lumped into the retail rates. We also don't address storage costs. We're really just looking at the bill savings portion of the equation to see how those various elements of rate design contribute to those bill savings. So the high-level approach is to compute utility bill savings from behind-the-meter storage across a range of rate structures and load shapes, which I'm going to be detailing in the following slides. So there are two key rate design features that impact the bill savings from behind-the-meter storage. The first is the demand charge. So the demand charge, as you know, is a portion of the electricity rate that's dependent on the customer's peak load level in kilowatts. So a storage system can reduce the demand charge by discharging during the customer's peak load time. The demand charge savings are really going to depend on the size of the demand charge. So large demand charges are going to lead to greater demand charge savings, but also on a variety of other features. Demand charges can be non-coincident or based on peak demand during predefined peak periods. And this is going to impact how well storage can reduce the demand charge. Other factors that can affect how effectively storage can reduce the demand charge are going to include the timing and duration of the demand charge peak period, the averaging interval for measuring billing demand, any kind of seasonal variation in demand charge rates, and finally ratchets, which effectively set billing demand to be at least some percentage of the last 12-month peak demand. The second rate design feature we're looking at is the energy charge arbitrage value from storage. So basically, this is the bill savings created by charging the storage during lower price periods and using it to offset grid purchases during higher price periods. So clearly, the value of these savings are going to depend on the price differential between the high and low price periods, as well as the daily, monthly structure of price variability and the duration of the high and low price periods. Each of these three features will vary among different types of time-varying rates, including time of use, critical peak pricing, real-time pricing, as well as net billing for PV. So in this analysis, we try and understand the relative significance and manner in which each of these rate design features impact the customer economics of behind-the-meter storage. So moving on to the data and methods. So let's go through the data, the load data that we use for the demand charge analysis first. So the demand charge analysis focuses on commercial customers. So even though there are residential customers that have started being exposed to demand charges are still much more common among commercial customers. We also have access to rich commercial load data. So we made use of a data set that was collected and published by NLX, which was formerly ENERNOC. And this consists of 5-minute interval load data for 100 commercial customers over a single year. So we selected 3 representative customer loads with very distinct load shapes and features. So the first is a shopping center. The second is the same shopping center, but we've added a PV system to it and looking at the net load there. And the third is a manufacturing plant. For the PV system, we constructed the PV profile using simulated data from NREL's National Solar Resource Database and the system advisor model from NREL as well. We sized the PV system to be able to generate about 50% of the building's annual energy consumption, and we're going to see what each of those loads look like on the following slides. So the 3 individual customers chosen are located in Chicago, but previous analysis that we've done of commercial demand charges has shown that building type is much more important than location in determining those demand charge levels. So on this slide, we see the average seasonal loads for the 3 selected customers, which again were selected so that the analysis captures a range of load shape attributes. These aren't necessarily representative of these 3 customer types, because of course there's a large variety of manufacturing, of shopping centers. But we're really just using these three as examples which highlight particular features of load shapes that are common through all customers. So the shopping center tends to have regular loads throughout the year with a wide midday peak load. When we add PV to that, the net load displays these skinny peaks that are shifted to late afternoon and evening times, as we see here. The manufacturing load was selected due to its relative flat load shape, which is stable throughout the year. So for the demand charge modeling, we're calculating the demand charges with and without storage. We used a reference demand charge of $7 per kilowatt, which is non-coincident, using a 15-minute averaging window with no ratchet. So this $7 level was based on median demand charge levels from our analysis of the OpenEI utility rate database, which compiles rates for a large number of utilities throughout the country. We also calculated demand charge savings for a number of alternative demand charge rate designs, including varying levels ranging from $2 to $15 per kilowatt. We looked at 3 different peak period demand charges with varying peak period definitions, 8 to 6 p.m., 8 a.m. to 6 p.m., noon to 6 p.m., and 5 to 10 p.m. We looked at averaging intervals ranging from 5 to 60 minutes. We considered 2 seasonal demand charges using a winter and summer peak, and finally considered ratchets, a couple of different kinds of ratchets. So the storage was modeled using a perfect foresight dispatch algorithm using this Homer grid software, which is a commercial software. It was optimized to reduce the demand charge only. So the storage capacity of the system was sized to meet 20% of the customer's peak annual load. And we modeled 1 hour, 2 hour, and 4 hours of storage. So 4 lengths or sizes of storage. And then we compared the demand charge savings across the rate design, primarily in terms of annual bill savings per kilowatt of storage capacity. So dollars per kilowatt year. For the energy charge arbitrage calculations, we considered 4 rate designs. So the first is time of use rates. And we analyzed a range of time of use rate structures. We considered a critical peak price, or CPP, where a number of hours in the year are announced in advance as very highly priced hours. We considered real-time pricing, where we set the volumetric energy rate to the hourly day-ahead wholesale market price for 9 different electricity markets in the US. And finally, we looked at net billing for PV, where exports for PV generation are compensated at a price that is 1 to 10 cents per kilowatt hour lower than the retail rates. The storage modeling in this case was optimized for energy arbitrage only, and we assume an 85% round-trip efficiency. For the 3 time-varying rate structures, including time of use, CPP, and real-time pricing, we assume that the battery can be fully charged in the 2 lowest priced hours and fully discharged in the 2 highest priced hours. For net billing, we assume that the storage can be fully charged from PV generation each day that would otherwise be exported to the grid. And because the energy charge savings are largely independent of the underlying customer load shapes, the results that we present aren't specific to either residential or commercial customers. Given that the longer duration storage systems are going to lead to larger savings, we compare energy charge savings across rate designs, primarily in terms of annual bill savings per kilowatt hour of storage capacity. All right, so now finally let's look at some results. starting with demand charge savings from behind the meter storage. So the first thing to note here is that the demand charge savings from storage vary by load shape and by the duration of the storage. So note that there are two metrics used to measure storage capacity. The first is the power measured in kilowatts, and this is really the maximum discharge power provided by the storage system. And the second is duration. How many hours can that discharge power be maintained for? So the figure we see here on the left shows the demand charge reduction efficiency for the three load profiles and for three load durations, represented by three colors. Here, I define demand charge reduction efficiency as the demand charge reduction divided by the storage system size. So, for example, a 100 kilowatt storage system, which is able to reduce the average demand charge over the year by 60 kilowatts, has a demand charge reduction efficiency of 60%. The demand charge definition we're using here is really our non-coincident reference demand charge. So one thing we can see from the figure is that storage can reduce the demand charge for the three load shapes we considered to different degrees. So specifically, storage is most effective at reducing demand charges for customers with narrow peaky loads. So for example, for the customer with PV, which tends to create those narrow peaks in early evenings, as we've seen in those load profiles, even storage with shorter durations can be effective at shaving those narrow load peaks. For customers with flatter load profiles, the manufacturer customer, for example, in our case, storage can't really sustain the required discharge rate to reduce peak demand substantially. Of course, longer duration can be more effective at reducing demand charges than those shorter duration storage. And this is simply because longer duration can sustain discharge rates longer, and this potentially reduces wider peaks, though there are diminishing returns to duration. So the figure here shows the demand charge reduction efficiency for the reference demand charge design. These customer differences in demand charge reduction efficiency really hold across most of the designs that we considered in our analysis. I do want to emphasize that the focus of the remainder of the analysis I'm going to be presenting is on the change in demand charge savings from these baseline levels when we modify one single element of the demand charge design at a time. So in this slide, we're looking at how the annual bill savings from the demand charge reduction compares for different variations of various demand charge designs as compared to the reference demand charge design. And again, that reference demand charge design is a non-coincident constant demand charge level of $7 per kilowatt. So the figure here on the left shows the annual bill savings in dollars per kilowatt of storage capacity for a range of a number of demand charge designs, including the demand charge rate level here on the left, the coincident peak definition, the averaging interval, whether they're seasonal rates, as well as the presence of ratchets. And I considered various definitions for each of these demand charge designs, and the range in the annual bill savings seen in these bars are represented, the range are represented by these orange bars here. So if, for example, I considered demand charges of $2 per kilowatt, leading to about $12 in annual bill savings, as we see here. And I ratchet this up to $15 per kilowatt, which leads to about $95 in annual savings per kilowatt. When comparing each of these elements of the demand charge designs, we see from this figure that the demand charge rate is really the most critical design feature in determining the annual demand charge savings. So though most of the demand charges available out there are within this range of $2 to $15 per kilowatt. There are a few that have higher demand charge levels, some as high as $30 per kilowatt or even more in some utilities. So, of course, in those cases, the value of annual bill savings from storage can be significant, and this really provides a strong incentive for adoption of behind-the-meter storage in those utility service territories where those demand charges are really high. Peak period demand charges, where the billing demand level is measured during a specific predefined peak period, can really boost demand charge savings by about 80% in this particular example when those windows are relatively narrow. The averaging interval also has a distinct impact, plus or minus about 20% in our example, with greater demand charge savings for shorter averaging intervals. Again, the averaging interval is the period of time in which the customer's demand is averaged to determine the billing demand level. And finally, we see that the seasonal rates and the ratchets of the demand charge really have very limited effect on bill savings for the variety of definitions of each of these that we've considered. So the following set of slides are going to delve a little bit more deeply into the demand charge design elements so that we develop more of an intuition behind these trends and why we're seeing these trends. So in the previous slide, we saw that the demand charge level was the single most important factor in determining the annual bill saving levels. So I thought I'd show a map of demand charge levels in utilities throughout the US. This map here on the right, which was developed by NREL, the National Renewable Energy Lab, shows those levels with darker colors representing higher levels. So we see dark brown in many parts of California here, but also in some of the smaller utilities and states, mostly concentrated in the west of the United States. Much of the country is shaded in these lighter colors, which indicates pretty low demand charge levels. So indeed, the demand charge rates really can vary significantly by utility and customer class, and the level of the demand charge is going to really depend on a variety of factors, including the underlying utility costs that the demand charge is trying to recover, the cost allocation across customer classes, and which specific cost elements are covered through the demand charge. For larger commercial industrial customers, the demand charge can be 50% or even more of their total electricity bill. Prior studies looking at the demand charge levels throughout the country have identified demand charge rates of $10 to $15 per kilowatt as a typical threshold for behind-the-meter storage cost-effectiveness, but this is really going to depend on the cost of storage, which still varies greatly and is falling fast. Demand charge rates at these levels are occurring in most states, so that $10 to $15 level, for at least a portion of the utilities and rate structures offered. Our own analysis of the NREL utility rate database found that about 80% of all demand charge rates fall between the $2 and $15 per kilowatt level, with an overall median of $7 a kilowatt, which is why we use it as our reference. So we've already seen that storage is generally more effective at reducing demand charges when these are based on peak period demand. And in this slide, I wanted to introduce why that is. So again, the peak period demand charge is an alternative demand charge rate so it's an alternative demand charge rate designed to non-coincident demand charges, and they're based on maximum demand during designated peak periods. So these peak periods, when present, typically begin at some point between noon and 2 and end between 6 and 8 p.m., but the timings can really vary considerably from one utility to another. So what these peak periods do is effectively create a skinnier demand peak, which makes it easier for storage to reduce the billing demand. So in the figure here on the right, we see an example load during 1 day period showing, so that load is shown in the red curve here. If storage is dispatched to reduce a non-coincident demand charge, shown in the green line, here, it can only reduce the demand by this much, right? So this amount is what storage can reduce if it's a non-coincident demand charge. However, if storage is dispatched to reduce the demand charge during the peak period, which is in this shaded time, storage can more effectively reduce the peak billing demand because it doesn't need to maintain that discharge rate for as long a period. So here we see in the blue line that we can maintain, so we can discharge during these peak times for kind of a longer period of time. So naturally, demand charge reductions from storage are going to be greater for shorter peak period windows. Of course, these reductions are also going to depend on the timing of the peak period and the underlying load shape during that peak period window. So if the timing of the demand charge peak period coincides when the load is ramping up or ramping down, the resulting sharp load peaks inside the window can really more easily be clipped by storage. So now let's look a little bit more closely at why shorter averaging intervals lead to greater demand charge savings. So demand charges are typically based on demand which is averaged over a 15-minute chunk of time, but these can be averaged over intervals ranging anywhere from 5 minutes to an hour. What happens when you have a longer averaging interval is that the billing demand variability is smoothed out. So storage really has less of an opportunity to cut those short peaks. So in effect, longer averaging intervals are a proxy for storage, and this erodes the opportunity for further demand reductions from storage. So in the figure here on the right, we see the customer's load average over 5-minute intervals in the blue line and over 1-hour intervals in the red line. So the dispatching of the storage is exactly the same, shown in the green line, but the resulting demand charge savings are lower with the 1-hour window than the 5-minute window. And so that's what we see here. And again, this is because some of that smoothing results in fewer peaks, and therefore storage is only able to reduce the demand charge by this much. Whereas with the 5-minute interval, it can reduce those really variable loads and these peaks, and it can more effectively manage the billing demand. So the significance of the averaging interval is really going to differ across customer load profiles depending on how noisy or variable those load profiles are. There won't be too many differences in demand charge savings for very flat or smooth load profiles for different averaging intervals because averaging over a longer time period isn't going to further smooth the load shape. So now let's look more closely at the other main source of value from behind the meter storage, which is the energy charge savings. So again, energy storage can be used to displace the higher price consumption, for example, by charging the storage system from the grid when the prices are lower, and then discharging the storage to displace the customer's load when prices are higher, and this really avoids higher cost purchases from the grid. This, of course, is a form of arbitrage. So here we look at various forms of retail rate designs that enable energy charge arbitrage. So similar to the summary figure that I'd shown for the demand charge savings, here we consider annual bill savings for different types of time-varying rates. Note that the y-axis is dollars per kilowatt hour as the bill savings metric rather than dollar per kilowatt in the case of demand charge savings. And I did this because arbitrage savings really scale with duration linearly in many cases, up to a point, of course. And so we can use this metric in this case. And we're going to be comparing both the energy charge arbitrage with the demand charge savings in one of our grand finale results slides. Again, for each of the rate design types, we consider a range of rate definitions from current utility rates. So for the time of use bar, for example, we're looking at a large variation in the annual bill savings, depending on how these time of use periods and peaks are defined. This really is going to depend on the peak to off-peak price differential, as well as the seasonal definitions, the number of summer versus winter months, for example. Very small price differentials, as for Rocky Mountain Power's large general service rate, for example, are going to lead to very low arbitrage savings. And vice versa, when you have a large peak to off-peak differential, that can lead to much more substantial energy charge savings. With critical peak pricing, which is often a time of use rate in addition to a number of very highly priced critical days, the arbitrage savings tend to be a bit higher. With real-time pricing, the annual bill savings from arbitrage are more limited when the energy charge is set to equal the wholesale prices, because the average peak to off-peak spreads are relatively low. So we're going to look at this in a little bit more detail in a following slide. For net billing, where one would charge a storage system instead of exporting the PV generation to the grid at a lower price, the daily arbitrage savings are driven by the difference between the retail and the PV grid export rates. The latter can potentially be based on some construct of avoided costs. Now, let's look at the mechanics behind energy arbitrage. How really is storage dispatched to minimize bills? So for time of use, critical peak pricing, and real-time pricing, the strategy is pretty similar. Bill savings from storage are achieved by charging during the low-priced hours and discharging during the higher-priced hours. This is shown in the figure here, where the gross load can be seen in red, and the combined load plus storage dispatch is seen in green. We see that during the predefined peak time of use period, the combined load plus storage is lower than the gross load as the storage is discharging, and then the storage starts charging after the end of the peak TOU period, which is what we see on the top figure here. With net billing, what we see is that storage attempts to reduce PV exports. So when the red line on the bottom chart is negative, this indicates that the PV system is exporting electricity, and when it's positive, there's a net load, so a net consumption. So in this example, the net PV load profile is shown in red, and the load plus PV plus storage profile in green. So the hours when, again, there are negative loads, these are exports, the storage is charging to reduce those exports. So focusing on time of use rates, we found that time of use arbitrage opportunities vary by state and utility, primarily reflecting retail rate design choices. So I created this map here by selecting the residential time of use rate for the largest utility in each state, ranked by number of residential customers, and then calculated the annual energy arbitrage bill savings per kilowatt hour of storage capacity. Opt-in time of use rates are offered for residential customers by the largest utility in 38 of those states, 38 states. The map shows arbitrage value for residential customers only because commercial customer rates often have demand charge elements as well, which makes the total bill savings dependent on the load profile. Whereas when there's no demand charge savings, we can kind of abstract from any particular load profile. So the map, of course, focuses on the largest utilities, so it's not indicative of the other utilities in each of these states. And in fact, there's a wide variety of time of use, peak to off-peak differentials, which exist within each of the states. So the main thing we note here is that there's no geographic trend that we can observe from the map. And this is because time of use rates are really only loosely defined on wholesale electricity prices. So states which have similar wholesale electricity prices won't have similar time of use rates necessarily. There are more limited set of critical peak pricing rates. So instead of showing a national map, here I instead chose to show a sample of commercial and residential critical peak pricing rates, illustrating the range in bill savings from storage. Note that some of the commercial CPP rates do have a demand charge element to them, and those aren't reflected in the values shown here. So the figure shows the arbitrage value from storage for each utility's rates, where each bar represents a single utility's critical peak pricing rate. And the value is separated into the value from the time of use arbitrage on non-event days in orange and critical peak event days in blue. The green circles show the number of event days, and the dark diamonds show the CPP rate level, which ranges in this case from 30 cents to $1.40 per kilowatt hour. With this very wide variety of CPP rates, there's of course a wide variety in arbitrage value from storage, ranging from $4 to $56 per kilowatt hour of storage annually. The arbitrage from the CPP events typically comprise 1/4 to 2/3 of overall energy charge savings. So you're really using that storage during those maybe 10 to 20 events per year, and that storage is constituting a large portion of the value over the year. Arbitrage value on those CPP days could be lower if customers are independently reducing load below the storage capacity during those events, in which case storage would not fully discharge, though the incentive to do that is going to be lower with a storage system. So we also looked at the potential arbitrage savings from storage, assuming that customers are exposed to the day-ahead real-time price for each of these 7 electricity markets. We selected 100 random price nodes from each of these ISOs from as far back as 2009, in some cases a bit more recently, through 2018, to capture a large range of market conditions and assume that the storage can charge and discharge in the 2 highest and lowest price hours of each day. Real-time rates are going to be most common among industrial customers and are really pretty rare other than that. Maybe there are a few pilot projects for residential and smaller commercial customers. The figure here shows a box plot of the range of annual arbitrage value per kilowatt hour storage, and the range is going to represent the variability from one year to the next. There isn't a very large range, and the variability across years and markets is also relatively low. Some years at ERCOT in Texas, Cal ISO, and PJM in the northeastern areas had high daily price variations, and that's led to some higher arbitrage values in some years. We could potentially see higher hourly variability and hence arbitrage value if retail real-time pricing were also going to include more temporal variability in marginal distribution costs, for example, or if we were to have higher levels of PV penetration. So this is the grand finale results slide that I was mentioning a bit earlier. We've looked at most of these rate design elements individually. So here we compare how the bill saving ranges compare across demand charge savings and arbitrage savings together. So the figure here shows the range in annual bill savings from the demand charge savings on the left for the 3 load profiles considered for 3 storage durations using the reference non-coincident demand charge design with the $2 to $15 per kilowatt range. On the right side, we see the ranges in bill savings from arbitrage that we've looked at before. But we show these energy charge savings in terms of dollars per kilowatt of storage capacity in order to allow the comparability between the two. The range in energy arbitrage savings reflect the specific set of rates that I featured in the previous slides. The main point from this slide is that some time of use rates and net billing rates offer bill savings that are comparable or greater than the demand charge savings, depending on the retail rate design. A more subtle point is that the relative importance of the demand versus energy charge savings from storage also depends on the duration of the storage. Energy arbitrage savings scale more or less linearly with storage duration, while demand charge savings will face a diminishing returns to scale, which has implications for rate design and behind-the-meter storage adoption as longer duration storage becomes more economically viable. So let's finish up with some quick conclusions from this work before our final slide. So first, it's not just about the size of the demand charge, which has been the focus of previous research. There are other rate design features which are very important to understanding the customer economics of behind-the-meter storage for both residential and commercial customers. This is particularly important in this era of changing rate designs and PV compensation mechanisms. And in particular, peak period demand charge designs, demand charge averaging intervals, and time of use peak to off-peak energy price differentials are all significant to determining the customer bill savings from storage. The details of the demand charge design are more important for some customers than others. So for example, the demand charge reduction will depend on how peaky or variable the customer load shape is, as well as the timing of those load peaks. Among the rate design elements and customer types considered, demand charge savings can range from $8 to $143 per kilowatt of storage capacity per year, with arbitrage savings can range from $4 to $112 per kilowatt of storage capacity per year for a 2-hour duration storage system. With longer duration storage, energy arbitrage savings can be sometimes substantially larger than demand charge savings. And again, arbitrage savings roughly scale with storage duration, whereas there are diminishing returns to demand charge reductions with increasing storage durations. Okay, and with that, I wanted to conclude this presentation part of our webinar. You can find our contact information here if you'd like to email us about anything. I've left some time for question and answer, about 15 minutes or so. Andrew's been collecting some of your questions, so we'll start with that. I'm also happy to talk a little bit about aligning interests between storage, customer bill savings, and utility cost savings as well. So if you haven't had a chance, you can ask questions in the chat feature of the webinar, and I think it's on the lower left of your screen.
Great, and we do have a number of questions that are coming in, so we'll jump right into it and try to see if we can get through all of these. So just a couple of clarifying questions just to begin with. So the first one was, could you just tell us again a little bit of what's the difference between the demand charge reduction when it's measured in kilowatts and the demand charge reduction in dollars per kilowatt?
Okay, so when looking at the demand charge reduction in kilowatts, we're just saying, okay, how much can the storage system reduce your demand charge without looking at a dollar value. So again, if your peak demand charge is, if your peak demand is 100 kilowatts and your storage system is able to reduce your peak demand to 60 kilowatts, that's a 40 kilowatt demand charge reduction. When considering the dollar per kilowatt values, we're translating that kilowatt into a dollar value, and that's going to be dependent on the demand charge level in dollars per kilowatt. And so in this example that I just gave, for example, a $10 per kilowatt demand charge would lead to 10 times 40 kilowatts, so $400 per year of savings.
Okay, great. And one question, a technical question. So you showed storage decreasing demand. Did you also account for the potential increase in demand that might occur to charge the storage, and was that factored into the analysis?
So yes, it was. So the increase. So two things. One is you would never charge your system during your peak consumption. So you would never increase your demand, your peak demand by charging it at that time. For one, for arbitrage, you do charge your storage system, but you do that during off-peak hours, and so you're again taking advantage of those low-priced off-peak hours. But that won't impact your peak demand if it's during your off-peak hours as well.
Great. Okay. And then we have, why was it that you sized the storage PV to 50% of the demand? Sorry, of the annual energy.
Right. So for commercial, it was arbitrarily chosen. Really, we were looking to just have a PV system that would create those skinny peaks that I presented in an early slide. We could have chosen a different size. We have seen, depending on the available roof space, we have seen some PV systems that are anywhere from 25 to 50% of annual load. But it was kind of arbitrarily chosen, and in the end, what we care about is the load shape, net load shape.
Great, thanks. Hey, Naeem, just in terms of a technical thing, my ReadyTalk just crashed, and if you can promote me to presenter again. I have questions written down for some of them, but if you could do that real fast while we talk.
Sure.
Great, there it goes. So the next question is, do we assume that a customer with storage stays on the same rate as they were on without storage, or is there any sort of opportunity for rate switching for customers when they add storage, and what would that do to the demand savings?
I'm going to ask you to repeat it just because I'm trying to promote you here.
Okay.
1 second. All right, I promoted you again. Okay. Sorry, could you repeat that question?
Yeah, so the question was just, do we assume that a customer with storage stays on their same rate as they were on without storage? And what sort of opportunities might there be for rate switching when you add storage?
Yeah, so that's a good question. I did assume that the customer was on the same rate before and after adding storage. One could potentially take advantage of a rate that's more advantageous, so even lower bills when switching to another rate. And so in that case, we might see slightly larger savings per kilowatt of storage. That said, it's difficult to this is going to be really dependent on the customer's load profile and what rates are available to these customers. And as we know, Some utilities, especially for commercial, industrial customers, have a wide variety of rates. And so this is where perhaps some tools provided by the utility or others could be particularly helpful in understanding how particular rates may impact their bill savings. So to summarize, yes, no, we do not take that into account in this particular analysis, and switching from one rate to another may enhance your bill savings.
Great. I'm going to do two more sort of technical questions, and then I think we should move on to this discussion of sort of the alignment of the customer bill savings with sort of utility system cost savings, because you're getting a number of questions on that part of it. So
Sure.
a couple more before we jump into that. One was just for all of the energy charge savings, you didn't really talk about what load shape you used. Is there any influence of the customer load shape on the energy charge savings?
Yeah, so basically we didn't use any particular load shape for our energy charge savings, and this is in part because we assume that the storage system can be fully charged during the off-peak times and fully discharged. So we assume that during the peak times. So the assumption there is that the customer has enough load during those peak times to fully discharge their storage system to offset that load. In cases where a customer would have a load that doesn't allow the storage system to fully discharge during those peak times, then you wouldn't take advantage fully of that storage system, and so the arbitrage value would be lower. In that case, however, the customer would probably end up installing a smaller storage system in the first place, and to be able to fully discharge their storage. So again, to summarize, we did not use any particular load profile for the energy arbitrage calculations, but we did, but we do assume that the storage system can fully discharge during the peak load.
And then one last question before we move on to the aligning interest part is, just could you say how do these rate designs interact with net metering rate design?
Right. So with net metering, which is for solar, net metering is effectively a proxy for grid storage, right? Because you can export electricity, rolling your meter back and use it later on. So using the grid as storage, as has been said before, and so storage, the value from storage, there's no additional value from storage with net metering, because you're not able to kind of extract any further value from net metering, since net metering itself is a proxy for storage. So there's no kind of added benefit to storage with net metering if you're on a time invariant rate.
And then net billing is an example where you do have an opportunity that arises with storage, correct? And that's sort of a variant on the net metering.
That's right. So net billing is a different PV compensation mechanism. Your export, so everything that you inject into the grid, you're compensated at a lower rate than your retail rate, and that's where storage can provide some benefit. Instead of injecting into the grid, you use that electricity to charge your system, and then you discharge it at a later point to offset your consumption.
Great. Okay, so now kind of moving into this discussion of sort of aligning what the customer bill savings are and what the system cost savings are. So I think the first question is just that rate design in general needs to sort of focus on that overall system costs and,
right,
and not necessarily be designed to make storage cost effective. And so to what degree do these different rate designs align with system costs?
Yeah, so that is difficult to answer. It's going to be utility specific. So in some cases, the alignment might be fairly good. In other cases, not so good. Because we see such a large range in bill savings, unless there's an underlying large range in utility savings, it's unlikely that there is that there is a perfect alignment in terms of cost savings. One more thing to note is that even if there is alignment in cost savings and bill savings, perhaps the way the storage is dispatched is not a optimal storage dispatch from the grid's perspective, right? So if even if, let's say that the net costs were equal to the bill savings, there could be a way of dispatching that behind the meter storage that would lead to greater bill savings and greater grid costs. And I think I'm gonna cut the discussion here just because we're approaching the end of the hour. And with that, I'd be happy to answer questions by email as well. So feel free to reach out to me or to any of the authors by email. Again, the slides that were shown here are available on our website. If you just Google implications, rate design, storage, Berkeley Lab, those slides should pop up. And I wanted to thank you all for joining today.